let's go there. So, see. I can go a little further. Yeah, just yeah. Okay, okay. Thank you. Alô, alô. Bom, pessoal, bom dia aí para todos e todas. Nós vamos fazer essa sessão em inglês, tá bom? Para que ele acompanhe junto conosco, tá bom? Well, good morning, everybody. It's a pleasure for us to have Dr. Min here at COPY once again. And it's an interesting situation today because before, when we organized a meeting like this, we had a whole lot of people in the room. Now we have some people in the room, and we have a whole lot of people everywhere. Yeah, that's something different and interesting that we have today. Well, today we have here Dr. Min, who is a professional working especially on the area of solid oxide fuel cells and solid oxide electrolyzers. And he's a person who has interacted with us here at COPY and with other people in Brazil for several years. So I have prepared a small presentation to show a few things about his interactions with us. And so I'd like to show this before I give him the floor. So first of all, I'd like to say that we have nowadays a collaboration with colleagues from the University of São Paulo, from São Carlos, USP São Carlos, and also colleagues from Italy, from Messina in Italy. And in this project, we are working on solid oxide fuel cell that works with ethanol, because we have developed the direct utilization of ethanol in solid oxide fuel cells. And then I brought something to show. Would you mind to stay there? Because I think you will see it better just for now. Okay. So, well, it's really a pleasure to have here with us somebody who is really internationally well-known in this area, a person who has been working for decades on the same area of solid oxide cells, who is now at the Center for Energy Research at the University of California, but who has been at General Electric and Honeywell Allied Signal for several years. It means that Dr. Min has developed solid oxide cells with research in an industrial environment and also in an academic environment. So he has this ample experience in this area. And you know, he was here in 2004 when we created what we call Rede Pacos, Pacos Network. And we made a seminar here to create this Pacos network. And he made a presentation. These are people who worked with us at that time. And then he came once again when we held a seminar at Costa do Sauípe in Bahia. And once again, he interacted with us, with our researchers and students. And then we made another conference in Búzios this time. And Dr. Min was also with us, and this already sixth seminar of Rede Pacos, this Pacos network. It was not only that. In 2016, he came for Symposium Matéria. So it was a congress that we organized at the Museu do Amanhã here in Rio. So once again, he gave a course, and he gave also a talk during the conference. And then once again, when we organized the World Hydrogen Energy Conference in 2018, which was the biggest WEC conference held until today, he was here with us. He patiently listened to the Minister of Environment of Japan, and then the minister heard him talking to us about oxygen production on Mars. How interesting, isn't it? So using solid oxide cells. And by presenting this, I would like to say that it's not only an academic interaction. It's something that it's important for us here at the university, but also for the country, for Brazil. Because you see, people like me are people who foster these areas within us. Of course, we have other people doing this from abroad, and several professionals from Brazil too. But I would like to thank very much Min for all the interaction that we have been having all through these years. And you see the results, for example. Brazil produced a roadmap on hydrogen in 2005. The Brazilian Hydrogen Association was created in 2017. The WEC, the big conference, WEC, was held in 2018. Nowadays, 2023, we are working in Brazil on a national program on hydrogen, you see, which will really establish the way Brazil will deal with hydrogen energy from here on. So I mean, these actions, although they look a simple interaction, they are very important to, make things happen in the country, in these scientific and industrial areas. And it's not only academic work, it's not only conferences or regulation that comes in the country, but you see, these are the member companies of the Brazilian Hydrogen Association today. So it means that the effect is much larger than we can imagine. So all these companies today, they are working within the Brazilian Hydrogen Association to make hydrogen energy happen in Brazil. And very recently, in May this year, we held the third Brazilian Congress on Hydrogen. It was held in a small city close to Rio called Maricá, and it was a surprise to us. It was the first Congress we held after the pandemic, and we thought, well, maybe we'll have 400 people in the Congress. But we had 1,750 people in the Congress. It was twice as much as the WEC conference. We had, parallel to the conference, an exposition of companies where 4,000 people visited during the 3 days of the conference. So I'm saying this to thank very much Min for all the effort he has done in this collaboration with us, and to invite him now to speak to us once again. Thanks a lot, and the floor is yours. Okay.
Well, good morning, everyone. My great pleasure to be back in Brazil. You know, I used to talk to Paulo and say, well, Brazil is one of my favorite countries. So any opportunity I come here, I will so see me so many times. But thank you, Paulo, for the kind words. You know, I met Paulo maybe 20 years ago or so, and we have a lot of collaboration and discussion a lot on different areas, not only, you know, on fuel cell or electrolyzer, but on everything. So it's my great pleasure to be here, and I'm glad that Paulo asked me to come and to give this talk, and thank you for the opportunity to speak today. I appreciate that. So today, by the way, some of the photo I never seen it before, so I need to ask you for a copy. Today I'm going to talk about hydrogen and solid oxide cell technology, two different project area, but they are closely related. My presentation will have two parts. In the first part, I'm going to give an overview of the recent activities in the US on hydrogen, clean hydrogen. Before coming here, I said, well, maybe you're also interested to know what is going on in America. I can tell you that very exciting time for hydrogen. We have a lot of significant activity over there. I will go through that. In the second part, I'm going to give a brief summary of what we've been doing at the University of California, San Diego, or UCSD. I always invite you, if you have a party in San Diego, please stop by. San Diego, very nice city in California. Anyway, the work on solid oxide cell technology mainly funded by the U.S. Department of Energy, or DOE. So that's why it's sort of like interrelated. What we funded by the government is relate to what we're doing on clean hydrogen. So with that, let me go to the first part of my presentation on hydrogen activity in the U.S. Well, in the U.S., you know, probably in the same thing in Brazil, they consider hydrogen as had the potential to play a key role in clean, affordable, and secure energy future. And currently, there's an unprecedented, not only on technology, but also on political and business momentum for the clean hydrogen. There are a lot of interest in clean hydrogen technology in the U.S. So the U.S. thinking, or probably that I say the government thinking now, it's just maybe at the time to scale up the technology and then bring down the cost, especially the cost of hydrogen, clean hydrogen for practical applications. So the U.S. set up, maybe a couple of years ago, set up, they call Earth Shot, but under Earth Shot, there's a number of other shots, they call it. So there will be hydrogen energy shot. I don't know whether you remember, but in the 60s, the U.S. They call moonshot to prepare to send a human being to the moon. So they want to duplicate that kind of initiative. They call all shot. But within the all shot, there are very many different shots. I don't know all of them. But one of them is a hydrogen energy shot. And the goal is goal is 111. That means that $1 per 1 kilogram of hydrogen in 1 decade, in about 10 years. So the U.S. aim at to produce very affordable hydrogen in, I think, 2035 or something like that, about 10 years now. So that's the goal. They have other goal to go to this, in 2026, we try to reach $2 per kilogram midway, and then. So a few years ago, the U.S., they put out what they call the H2 scale initiative. In this initiative, thinking about, the evolve all the, I'm sorry. All the possibility of hydrogen production and all the different uses of clean hydrogen, and then within that there's a connection infrastructure. So that the initiative they create, DOE created about 2 or 3 years ago, they call H2 scale, and many things that will support that initiative. And most recently, the more recent legislation developments on clean hydrogen. There are 2 legislation laws that come out in the US. The first one they call Bipartisan Infrastructure Law. The second one is Inflation Reduction Act. In the infrastructure law, that's included almost $9.5 billion for clean hydrogen, and out of that, $1 billion to develop the clean electrolysis, $500 million for manufacturing recycle, and $1 billion for what they call regional hydrogen hubs. I talk a little bit about that in the next few slides. And the law requires that the DOE prepare, develop what they call national clean hydrogen strategy and roadmap, very similar to what Paulo mentioned that in Brazil. I think DOE, just because of the law, they just issue that, I think they released this document, 2 months ago or something, 2-3 months ago. And for the Inflation Reduction Act, they include a significant tax credit, for example, for clean production of hydrogen, that $3 per kilogram. So let me talk about briefly about the U.S. National Clean Hydrogen Strategy and roadmaps. In the strategy, it lists out three strategy for clean hydrogen. The first one is targeting the high impact end use of clean hydrogen, for example, in industry, transportation, and residential application. The second strategy is reducing the cost of hydrogen. That I mentioned earlier, this is the one that they like to reduce that down to $1 per kilogram of hydrogen. And the third one is focusing on regional network. They're going to build hydrogen network called Hydrogen Hub that I will mention a little bit later on. So that is if you can get into the internet and get a copy of this, that's a long document with all the detail for this. Let's talk a little bit about regional clean hydrogen hub. The U.S. envision that they're going to build at least four to 8 regional hydrogen hub. What is a regional hydrogen hub? That they mean that just sorry, I keep pressing. There are 3 elements for that hub. It's not shown. But anyway, if you see the figure on the right-hand side, there are 3 columns. The left column is a producer of hydrogen, clean hydrogen. The right-hand side is the users of clean hydrogen. And the middle one is the infrastructure, the connection, connect all the 3 together. And the way the U.S. vision, the hydrogen hub is consists of on the left-hand side, on those, it's just a schematic. That hydrogen, clean hydrogen produced by various energy resources. It could be solar, could be nuclear, and could be fossil, but with clean carbon, with carbon capture. So basically, and on the right-hand side of that figure is on the user. We have residential, industry, transportation, and the one on the left corner, a little bit of the figures is show all the connection between all these 2 together. And the vision that in all these in the close proximity, so in the specific region, it's not like from one side to the country to the other side country. So right now, the U.S. already came out with the solicitation for hydrogen hub, and many states, or combined many states all together submit proposal. My understanding initially that's about 40 something proposal, concept paper, and if you don't know in the US, then right now all the proposal you need to submit what they call concept paper, like a mini proposal, and they screen it, review it, and then tell you, okay, they interest in your concept paper, so you encouraged to submit full proposal. So I understand that there's about 40 or something, 40, 50 proposal on hydrogen hub. And then now come down to about 20. So they down see it's like, and I can tell you that California as a state, we submit one proposal to build a regional hydrogen hub in California. And that will include industry, end user, for example, like even in California, they thinking of even like hydrogen for the port of Los Angeles or the port of Long Beach. So that is a very big project. As they plan that to have at least $1 billion for this regional hydrogen hub, and each of them require 50% cost share. So the total cost probably about $2 billion for each of the regional hub. And in California, for example, the state, because they want to have the regional hub in California, so the state provide the cost share. So the state put in $1 billion and the federal government put in another $1 billion to build it. So I don't know when they announce the winner for this, but probably sometime in the fall. The fall in the U.S., that means, September, October timeframe. So most of the DOE hydrogen is all coordinated through the Department of Energy in America. So they have, all the program, various programs, the R&D, of course, but they also have the project to do technology integration, validation, and demonstration. And even they have a project to deployment and even financial. You can get a loan from Department of Energy to build manufacturing and things like that. But one thing I like to point out is in DOE, they set up a number of what they call consortium. And we have hydrogen consortium, we have HNEW consortium, from what I know, ElectroCAD consortium. Many of the consortium consist of members from national lab, because they do some national lab working with other people to develop, for example, new material or protocol to test the electrolyzer or fuel cells, etc. So there are many of those consortium, and all the DOE projects require to work with those consortia to develop on the related technology. So that's, I think, all I like to talk about the US activity on clean hydrogen. Now let me move on to talk about the solid oxide cell technology at UC San Diego. At UC San Diego, we're working on various aspects of the solid oxide technology. We work on, I keep pressing the wrong button. We're working on solid oxide fuel cell power generation. We work on solid oxide electrolysis cell, or SOEC, for hydrogen production. And we're also working on reversible solid oxide cell for both hydrogen and electricity production. And probably you know that solid oxide fuel cell can be operated in reverse, become electrolysis. So it could be, a unit could be work in both direction, in both operation mode. Currently, I have 5 different programs at UCSD, funded mainly by Department of Energy. Here I list the 3 major ones. I have a program of development. This is SOC as a power source for energy storage and power generation system for electric aircraft. So this is a long-term. In America, they vision that in the future we use electric aircraft, so that they try to develop the power system for electric aircraft. So that's not simple, for airplane. All the requirement, not only weight, volume, cost, many other safety, very high. But this is just an initial research. So I got the funding from DOE to look at The funding here, I don't know whether you're familiar in the America, the Department of Energy, they have a section, section in the department called the APA-E, APA for Advanced Research Project Agency, and E for Energy. If you're familiar with the research in the U.S., Department of Defense used to call, they call DARPA, Defense Advanced Research Project Agency, and DARPA in general developed some sort of like futuristic technology. Actually, you know, internet is developed by DARPA. Many other technology developed by DARPA. So Department of Energy want to duplicate that, want to have APA-E. So this project considered a very high risk, very long-term, futuristic, and in general very competitive. We had to submit a number of, take a while before we get this project. And so this developed the SOC for electric aircraft. And then we have a project developed reversible SOC for both hydrogen and electricity production. In this project, we want to focus what we call distributed system. That means that it can be located low on-site generation of hydrogen, or put it on-site production of electricity or hydrogen in remote area where electricity or very difficult to transport to hydrogen to those area. So that, and then we have the third project is developed. I talk a little bit about that later on the. This is a little bit more R&D on the 3D cell structure and manufacturing process, but it's mainly for electrolysis application, SOEC. So let me summarize what we did on those projects. There are two parts of those projects. One they call technology assessment. The other one is the technology R&D. In the technology assessment, I keep pressing the wrong button. We have activity to do what we call comparative technology assessment. And the other part is techno-economic assessment or cost estimation. These days, and many of the DOE projects, we require to do that to show that our technology cost competitive. So a lot of work on this area. In the technology R&D, what we try to do at the university, we try to incorporate advanced material or engineering and processing into our in the current technology. So we've been doing, you know, like thin film technology, we incorporate nano material into our technology. We look at microstructural engineering, digital manufacturing, and Paolo mentioned earlier about we also very interested in direct utilization of fossil fuel, you know, like ethanol and methane or natural gas for different application. So I'm going to give a brief selected results of this work in our lab. So for technology comparison, this example, we compare different technology for hydrogen production. We compare solid oxide electrolysis cell with I think that the PEM polymer electrolyte and the current technology alkaline electrolysis. And then we also compare with the current industrial technology for hydrogen based on reforming. So these, we compare not only efficiency, we look at the different things like what the feedstock, the operation flexibility, safety, hydrogen purity. We look at all different aspects, at what the maturity of the technology. And if you get the full circle, that means that bare, if it's sort like that in the middle, that's sort like between better and that's really comparative worse if it's open circle. So in general, I just want to point out a few things. In terms of efficiency, actually solid oxide cell, we think the best compared with all the other technology. The worst is lifetime of the solid oxide cell technology still worse compared to all other technology. The other, you know, either they bear or somewhat similar. But if you look at the current technology, the reforming, you know, in general, there's a, you know, CO2 bad in same CO2 emission, not very good in terms of efficiency, and in terms of operation flexibility, I think it's not as good as, you know, like on other. So that's sort of like a summary. We submit a report to DOE assess on the technology report. So this is just a summary. We did the cost. We have to show to DOE well, our technology is cost effective. And this is just, I just took an example about, take out one about the stack cost. We estimated, of course, it's based on a lot of number of assumptions. And if you can see here, you know, the breakdown on the stack cost. For this case, we have a total stack cost about $236 per kilowatt. If you say, oh, what does that mean? You know, the currently the solid oxide cell technology could be cost between several $1,000s per kilowatt. So if we have this technology significant, we also did use this cost to calculate what the cost to produce produce hydrogen based on this stack technology. In general, we got between $1 and $2 per kilogram. So it looked very good. Looked like we try to, you know, sort of like close to meet the $1 per 1 kilogram of hydrogen. In terms of technology, let me give some example about technology. So first example is thin film technology. We develop a manufacturing process based on sputtering. All the cell mechanism from the thin film cell, that's all the cell component here, and put on the a porous substrate. Here we show that it's, we use AAO or anodized aluminum oxide, but in general, all the film done by sputtering, and here the microstructure, the cross section on the right, on the right hand side here, show this the oxygen electrode layer. The GDC, gadolinium doped celia, we use that at the interlayer between the oxygen electrode and the electrolyte. YSZ, yttrium stabilized zirconia at the electrolyte, and this nickel YSZ at the hydrogen electrode. And if you look, we have a high magnification here. You can see there's a porous nickel YC electrode. And this is a porous LSCF or lanthanum strontium cobalt ion oxygen electrode with a YC and so porous and fully dense, very thin GDC and YC. And the most important thing is we get a very good interface within the different layers. But one unimportant thing is fabrication. What the kind of performance we get from this performance from this sputter cell. And here the structure showing the lab, and on the right hand side is so example of the performance of the cell based on this configuration. And this show, for example, at 650, we got that more than 2 watts per square centimeter. If you know about the solid oxide cell technology, typically maybe about 1 watt per square centimeter at 800 degrees C. So now we reduce the open temperature and also improve the performance. So we're very happy with that. Not only that, by changing the oxygen electrode material from LSCF to LSC or lanthanum strontium cobalt perovskite, we get even better performance. We get more than 3 watts per square centimeter at 650 degrees C. And I believe that the best performance report in the literature at that low temperature on each stabilized zirconia-based fuel cell. Now, one important thing is scale up. You know, if you have good performance in the lab, in the small scale, can you scale up this process? Well, as you know, that sputtering process is not new. It's been used in solar industry. They make solar component cell by sputtering, make a large area. In the lab, we have shown that we can make in the lab, we have made it as big as 15 by 15. Actually, because of our sputtering chamber, that's the biggest we can make. But it's currently the solid oxide cell technology. The size of industrial size about 10 by 10 to 15 by 15. So we make it to the size that could be used for commercial application. But more importantly, we have shown that we can make a very uniform thickness of the thin film. And so here, if we take the center, we go from the center, go all the way to the diagonal here, and we measure the thickness of the here and then this is thickness of the at different location, and we got very good uniform thickness. It's less than 5 plus and minus 5% of the thickness. Okay, so that's about the thin film example of nanomaterial. We show you that the sputter electrode made by sputtering. It's shown that here. We draw that diagram here to show you that the way that our electrode is formed is we have a sort of like a column of zirconia, and the electrode sort of like form like a fiber coming out from the zirconia, just like this. So with this, the same thing for the oxygen electrode and the hydrogen electrode. So with this type of nano structure, that means that the very high active area for the electrochemical reactions. That's why we obtain very high performance for our cells. Another work we work on nano is based on the nickel exol nickel nanoparticle from the hydrogen electrode. Here's our cell design. We have a three-dimension hydrogen electrode support. I'm going to talk a little bit about that. And we have the electrode layer, electroactive layer for the hydrogen electrode. For the electrode layer, we use perovskite. This is very similar for the oxygen electrode, but we substitute some of it by nickel. So the nickel substitute perovskite have a structure like this. When under reducing condition, the nickel is absorbed onto the surface of the perovskite and form the nanoparticle. So we have these nanoparticle embedded in the perovskite structure. With this kind of nanostructure, the nickel not only prevent the nickel from agglomeration, and also minimize the nickel. In electrolysis, you have a lot of steam. Nickel can be migrate through the reaction with the water, become nickel hydroxide. So in this design, the nickel, if it's leaving, then all the nickel will come out to replace it. So that kind of the design, nickel also will make the hydrogen electrode very stable, durable, and also minimize any degradation due to the nickel migration, agglomeration. And also because of nickel particle distributed on the perovskite surface, it's very high activity for the electrochemical reaction. So you can get a very good action. And here there's some example in our lab to show the nickel solution. We prepare the powder that's with nickel substitute perovskite. We reduce the material under high temperature with the hydrogen atmosphere for certain time. And if you look at the CM, you can see all the nickel particle absorbed on the surface. Interesting that if you reoxidize it, you put the powder, reduced powder into air at high temperature, 6 hours. For example, here 6 hours, you can see that all the nickel particle redissolve into the perovskite structure. So like a reversible exsolution, dissolution behavior. So we're still working on this, and we try to look into the electrochemical performance and the stability of these electrodes. Here the example of our microstructural engineering and digital manufacturing. If you work in the solid oxide cell, if you use the hydrogen electrode or called anode, nickel YZ, the issues, one of the major issues that we call the reduction oxidation issue, because the nickel YZ, when it starts to, we use the current process use a random mixture, and tape casting uses random mix YZ powder with nickel oxide powder. So after firing, you get a structure something like this, right? And if you then the nickel oxide, when exposed to the reduced environment, nickel oxide is become reduced to nickel metal. It reduces the volume, right? It reduces the volume. That's okay. That reduces the volume. So, but the The one thing is when it's reoxidized, the nickel start to expand. You know, nickel become nickel oxide, expand. And since the zirconias have many wiggling because of the random mixture, so the nickel oxide expansion cause the crack in the or fracture in the YZ network, and that it in turn cause a crack in the electrolyte. So this cycle is called redox cycle and cause a cracking of the cell. So what we try to do is we engineer the structure. We say, well, now we don't want it random. How about we make the zirconia into a three-dimensional network like this? And then the nickel will be also three-dimensional network inside the connection, inside the YZ network like this, you know. And if you look one section that you see that the YZ form a frame and the nickel oxide YZ inside, so if you reduce it become like this, you know, reduce open, reduce the volume. But when you oxidize, the nickel oxide just oxidize within this space, and YZ already a strong network around it, so it can train cause any fracture. So this is our concept, and then you say, oh well, it's interesting then, but then how you make it? Okay? So we think, well, to make it, we have to use additive manufacturing. And one example I show you here is a 3D micro extrusion or aerosol jet printing. And here the example of these two techniques. This is how the machine look like, and brings. And then first you make like a checkboard of YC, and you fill in that with nickel oxide, and you make a checkboard of, and you do that, keep doing that, so you build up the structure. Okay? So that's in principle. How can we do it? Yeah, we can do it. So I tried to make a video about this, but I copy it and it didn't come out. But this is the micro extrusion, this is 3D printing. But this we did it like that. You can see the picture how we did it. Make different layer. And then we do a cross section to make sure that what is with printing is okay. So it came out very good. It showed the various thickness of different components. So we now, this only early stage. We're still working on to do firing and other characterization. So this is the last part of my. So we very interested in direct utilization because we don't need reformer for fuel like ethanol or natural gas. So that's the principle, that if you have direct utilization like the top wheel, you don't need reformer. And our thin film, we did direct utilization of ethanol and show very decent, very good performance. This is also at 600 kc, so we got very good for ethanol. Pure ethanol, no water in it. And we also did it with methane, and we got very good performance on methane. We got more than 2 watt per watt per square centimeter at 650 or at about 700 kc. And I believe that this is the best cell performance and dry methane report in the literature. So with that, I'd like to just give a brief summary that in the US there were widening and significant interest and activity in the clean hydrogen, and that activity mainly led by the government on DOE. And we work at UCSD mainly on solid oxide fuel cell and solid oxide electrolysis cell in support of those activities. With that, thank you very much for your attention. Appreciate that. More than happy to answer any question. Thank you. Yeah, okay.
These work, yeah. Well, thank you very much, Dr. Min, for your very nice presentation. I'm impressed with the results. This? What? Okay. Okay. Well, so thanks for your presentation. I'm very impressed with the results of power density. It's really high for these very low temperatures, isn't it? So I think it's a very important achievement for solid oxide fuel cells. And we might have questions from the audience or from the people who are away from here. If there are any questions, please feel at ease. We can discuss with. Meanwhile, I would like to know, Dr. Min, on this fabrication, because this is a very specialized and delicate fabrication procedure for solid oxide cells. Mm-hmm. Do you do it mostly in the lab, or do you have partner companies that help on this fabrication?
Yeah, this. On.
Okay, it's working. It's working.
It's working. You hear me? Yeah. Right now, most of the work is done in our lab, and currently we have a proposal to DOE to work with a company actually manufacture sputtering machine. They also supply machine for industry, for solar industry. So we working at them to transfer the technology to so like large volume and high production. So that is something we are looking forward to in the future. But as you know, that like I mentioned, sputtering process is not that big. It's very simple. You just put this. You have the target within the chamber. It's done at room temperature, and it's been done for industry like solar cell. They use it for making solar cell in large area. I think sputtering also do a lot of coating like window coating. So big machine for large volume production are available.
Okay. Talvez fosse bom você pegar o microfone.
Professor, thank you very much. For me, that I'm not a technician, I'm not an engineer, it was quite easy to understand because you were very clear on your explanations. I ask you this, Professor. How far are we from massive production and utilization of this technology?
Yeah, you have a very good question. I very hard to answer. Say, well, of course, you know that our work is only in the lab. We don't have. Okay, thank you. So our work is only in the lab, so we don't have. But you know, solid oxide electrolysis cell or fuel cell, there's some company in the U.S. Or around in Germany and other country, they make system. They make product, not commercial yet, but in the demonstration prototype system. I think the most important thing is to reduce the cost. Because, if you produce anything, it's too expensive, no one going to use it. So reduction of the cost is very important. For solid oxide cell technology, not important. Related to cost is the lifetime. Because you don't want it short lifetime, you have to replace it, then it becomes very costly. So you want to make sure that it have a long enough lifetime. So that is another issue that working. But in the literature, many companies they will run solid oxide cell for, I think some of them up to 100,000 hours. So. Hope that I answered your question.
Well, let me use your microphone. We have questions coming from people that are not present here. There is one question, for example, from Igor Barreto, who would like to congratulate you for your presentation and ask you about metal-supported solid oxide fuel cell. And what could you say about using the anode-supported or metal-supported solid oxide fuel cell?
I think, thank you for the question. Thanks. I think that's a very, very good question. Actually, the reason we start to use anodized aluminum oxide as a support, because that's a very uniform porosity, very clean surface for the experimental work. But actually, it's not a very good for the solid oxide fuel cell or electrolyzer, because it's not conductive. We need a conductor to conduct the electron. So we working on metal support. I didn't show it here, but we're looking into a process to make a nano nickel powder from a process, and they make a porous structure from that nano powder. And then we also working on commercial porous metal substrate, but we also we need to modify because the porosity for commercial porous metal is a very, very big, so it's not suitable for sputtering thin film. So we're working on both on those processes. So we're looking forward to replace the ceramic substrate with the metal substrate. So that's the down direction. And we have some success to that. We still need to work on, because the surface of the metal substrate need to be doing the cleaning to make sure that it's flat enough, all kind of issue when we make the deposit, the thin film on the surface. So we're working on the metal substrate, and we have fabricated some cell and deposit film on it, some of it working very well. So looking forward to to scale up and do more work on the metals.
Well, since we talked about metal support, what about the interconnects? How do you deal with the interconnects for your cells?
We have the stack design. I didn't show it here. I apologize because that's an invention disclosure. The lawyer told me that you can't talk about it until we apply. But in principle, what my principle is to move the interconnect, if you know in the solid oxide cell technology, you need to have an electrical connection from one cell to another. It's mainly in the hot zone. We like to move that outside the hot zone. Our design to move that outside the hot zone, so you don't have to worry about what kind of material you use. So it could be, because the interconnect is the most expensive part of the solid oxide fuse. So we like to move it out. Also, now you don't have gas channel on the interconnect. You don't have to, gas channel also issue with the interconnect. You have to prepare the gas channel so that you have uniform gas distribution. So it requires certain tolerance in the.
That's
right. So that our design, and I think DOE very like it. What DOE right now looking into things, I think that fit into what we're doing. First, they like to reduce the thermal processing in making the cell, making the fuel cell or the electrolyzer. Because right now tap casting, you have to coal-fire the component at 1300 degrees C, and sometimes it takes days, 1 week, 3 days to 5 days to complete the process. So that's very energy intensive. DOE actually looking for people to get rid of those because to make it cheaper, low cost to make the cell. The other one is they looking for interconnect right now. I don't know whether you work in the solar. You know that there's use a lot of chromium containing alloy. Chromium also come out from the alloy and poison the cell. So they need to do a coating. So the coating costs money too. So what DOE like to do is how you get a cheaper interconnect cost. You don't need coating. So we propose to DOE check out the interconnect out so you can use cheap material. So fit into what they looking on. So that's the thing that we have to do all kind of things to make the cost of the cell and so that you can produce hydrogen at $1 per 1 kilogram.
Well, what you mentioned about taking the interconnect out of the hot zone is very interesting, but it's quite a challenge, isn't it? So,
yeah, there's some challenge.
Yeah. There's some people also asking about exactly cost, what you spoke right now.
Yeah.
It's Alexandre Teixeira. He has remarked that he finds a wide variety of costs. So what can you tell us about this?
Well, the cost right now is just estimate, right? So you need to look at the assumption first, right? You have to know what assumption, what the volume production, what assumption, where fabricate. We did a lot of work. We assume since our manufacturing, for example, sputtering process not make for solid oxide cell yet. So we have to propose that here the manufacturing plan, how many people, what kind of machine, and we did all the costs of that. So this also is based on our process. our stack design. People may have different stack design, their cost different. So you have to look at what the assumption and what your, I know that all over the map, you can have all kind of numbers. But you know, these numbers, just a guy, give us a feeling that, well, it's not something too expensive. If it's something really, really expensive, then, you know, and also give us a guide where the costs come from, which part of what the major contribution to the total cost. So you can focus your work on that. For example, we did a cost for the cell or the stack. We found, you know, long time ago when I did at GE, General Electric, we found that the interconnect cost almost like more than half of the total cell cost, stack cost. So that means that you have to reduce the cost of the internet. So.
Correct.
Okay.
Well, maybe we should say here that fuel cells nowadays are commercialized in large scale in the world. In 2019, we passed the barrier of 1 gigawatt of fuel cell commercialized per year. Today, it's more than 2 gigawatt. So there's a lot of fuel cells being sold and bought all over the world. Yeah. And what we see is that in the last decades, let's say, there was a big effort on PEM fuel cells. Yeah. But the commercialization and utilization of solid oxide fuel cells has grown throughout the years. And that's what I would like to ask. I mean, what's your prospect for real massive utilization of solid oxide fuel cells in the future? Yeah. I mean, and for which main applications?
Yeah. Well, you know, I'm somewhat biased. But, you know, it's very difficult to know because the political and business environment change every year, right? So depends. But I believe that the technology will play a role in the future. When I don't know because it's, you know. But if I look back, you know, when I first started working on this, I said, well, oh, this interesting technology. You work it for research purpose, you know, never come, you know. But years later, longer than what I thought, but there you can see the solid oxide. If you know that Bloom Energy in the US, they have station fuel cell everywhere in the world. They have actually number installation in Japan, Korea, and in the US. Years ago, I never thought that it would happen. So it's coming, but slowly. I don't know when, honestly, because the interest of the solid oxide come and go sometimes, you know, not as. But I believe that solid oxide cell, one of the advantage of that is, you know, it's more efficient than other technology. Second is, and the fuel cell, it can be used for different fuel. Can use for ethanol, that's very applicable to Brazil. Natural gas can use that. You don't need a lot of cleanup like polymer fuel cell. So it have some advantage, of course, has some disadvantage too. But I think the main disadvantage is the lifetime still right now. I hope that with lower the open temperature, new design and other things, that we can prolong the life of the solid oxide cell. along with the low cost, then it make more attractive for practical application. Sorry, long answer.
You know, I mean, some people do not have very much patience with the work we do.
know.
I remember it was by 2002, I had a visitor at the laboratory, and I showed him what we were doing there with solid oxide fuel cells. And we had milliwatt production.
Yeah.
And then he asked me, don't you think it would be better if you work with something that produces more electricity? Wow.
You're right, yeah.
Today we're producing much more than that.
Yeah. Well, yeah, but look back, look at Bloom Energy. They got capital venture funding for, from my understanding, hundreds of millions for 20 years. So I know that some people really impatient with, with technology, takes so long. But if you look back, I'm thinking, I keep telling people, you look at the gas turbine technology. Gas turbine, I think it's only developed during the World War II, and it takes million of years, many years. And gas turbine only year what, maybe 50 years ago or something. I don't know. So everything takes some time. I think, of course, we should not overpromise, but we should not, sometimes you have to stick your neck out and say, well, okay, we can do it in 10 years. Well, you have to set the goal high enough so that you can try to reach it. If you say, okay, 20 years from now, so we all, right, you have to say, okay, 10 years we do it, then we sort it.
Yeah, here at the Hydrogen Laboratory at COPI, we have been working for several years on the direct utilization of either ethanol or methane. Yeah. And as you mentioned in your presentation, this is very interesting because it eliminates the pre-reforming to produce hydrogen. And so I think this is an interesting effort for us here in Brazil, but for other places too, isn't it?
Yeah. That the one of our objectives in the reversible, DOE wanted to do the reversible, but in the fuel cell mode, you can operate on natural gas. Of course, in the US, they focus on natural gas and ethanol, natural gas. And on the reverse, it can be produced hydrogen from water, from steam, from water. So that the reversible solid oxide cell technology we developed.
Yeah,
and we found that it can be done. I mean, in the small scale in the lab, it can be done. Of course, I'm not saying that's all ready for. There are a lot of things we need to deal with carbon deposition if you use direct fuel utilization. So
yeah, this was a main point for us because we have developed electrocatalyzers that resist to carbon coking and clogging. So we are able to use directly the carbonaceous fuel without having carbon coking and clogging. And then this is, I think, a very nice achievement, and I think it is. It has a good prospect to increase stack power and so on. So we were working on it. I have now, a question from Massimiliano Lofaro. It's a colleague from Itai CNR in Messina in Italy who collaborates with us in this Flex Power project. And he is curious to know about you, the interest that there is at DOE to finance projects on solid oxide cells regarding other technologies. I mean, how is the interest at DOE with respect to solid oxide cells?
You know, right now, solid oxide, I think DOE interests all three. They interest on polymer, they interest solid oxide, they also interest in alkali electrolyzer, that commercial, but they like to advance, you know, improve the, so they are all working on three. The polymer electrolyte, probably the same interest in the solid oxide, but you know, the DOE have been supported polymer fuel cell for a long time, and actually significant funding. So I believe that they try to shape a little bit of the, especially for electrolysis onto the solid, but I really don't know. I think right now depend on the application. I don't think that they divide it and so, oh, right, how many percent go to this, how many percent. I think depend on what, if you get a good idea and, you know, that.
But there is an important effort for financing solid oxide cells at DOE, isn't it?
Yeah.
Yeah. Okay.
Right.
Well,
actually, you know, right now DOE have a lot of funding to fuel cell energy. They have a big project to do electrolysis also currently. So there's several funding on some company doing solid oxide. But relative, you know, because solid oxide is a little bit newer to the, what we call the section of the DOE, they call energy efficiency and renewable, EERE. That's Sunita is part of that. Yeah. So they more work on the PEM for a long time, so that more. But recently, the significant number of projects on solid oxide.
okay.
And now, when they come out, a solid station, it covers everything. It covers PEM, covers solid oxide, you know, cover alkali. Of course, I don't know exactly, but I heard from some people told me that probably it's more solid oxide and polymer funding.
Yes.
And alkali, probably they should do it for, to make sure that it included, but I don't think that there's significant.
Well, I think what you mentioned here on electrolysis cell, solid oxide electrolysis cell is very important because it's high temperature electrolysis. So
right.
it is thermodynamically much more interesting.
Right.
So with a higher efficiency. So the new developments we have on solid oxide electrolysis cell, I think will bring us another level of efficiencies to work with electrolysis in the near future.
Yeah, like we did the efficiency analysis. I show the comparative analysis, different technology, you know, in terms of efficiency. Solid oxide cell had the best potential for high electricity.
Yeah, that's right. Well, I'd like to know if there is any other question from here or from the audience that is not present here. Apparently not. So I would like to thank very much once again Dr. Min's presence here with us. And after a while, we're going to take Dr. Min to visit our lab and to discuss a little more about solid oxide cells. So thank you very much.
Yeah.
Thank to all of you.
Yeah, thank you everyone for coming. Appreciate that. Thank you.